So good afternoon, ladies and gentlemen. This is the last session of the Nečas seminar on continuing mechanism this semester, and our speaker is Pavel Krejčí. Pavel Krejčí is an associate professor at the Department of Mathematics of the Civil Engineering faculty. He was also director of the Mathematical Institute of the Czech Academy of Sciences and many functions in the body of the Academy of Sciences, and he is a legend in the theory of hysteresis. And today his topic is again in hysteresis.
So, thank you for being for the kind introduction. So, ladies and gentlemen, very honored to be asked to give a talk here in this prestigious seminar. And I would like to show you some recent results that we got jointly with Chiara Gabrioli, who is also sitting here, about hysteresis porous media. This is Chiara's main topic of her likely fellowship that we got for 2 years at the Faculty of Civil Engineering of the Czech Technical University. And so we will continue working with this topic. So these are some preliminary results we have obtained recently. Now, why do we talk about hysteresis porous media? So there is enough engineering evidence that hysteresis porous media exists. The drying curves are very different from the wetting curves. So theta is the moisture content, the saturation, which is typically between 0 and 1. So the drying curves are different from the wetting curves. And please observe that there is a turning point. So C is something like the pressure. I will make this more precisely. So when here the pressure has a turning point, the pressure decreases and increases again. The starting slope is horizontal. So horizontal starting slope at every turning point. This makes the problem difficult. And I will explain why. Now, it's mathematical model. So we will consider the standard diffusion equation. Theta will be the fluid content, so saturation which is between 0 and 1. And obviously, I will go back. So there is a mass density positive, but we put the mass density, but we want to simplify the formulas. And so this is nothing but now this is mass conservation. The mass increase is compensated by the divergence of the flux. And so I denote by U the normalized pressure. So this is the pressure minus standard pressure divided by the standard pressure, something dimensionless. So U will be the pressure, theta is the fluid content, and it is supposed to be a hysteresis operator of the pressure. So this the picture that I was showing on the previous slide was giving an idea about how the hysteresis operator should look like. The flux is supposed to be proportional to the pressure gradient with the proportionality factor, which contains the permeability kappa, positive, which may depend on the saturation degree. This is what the engineers insist on. They say you cannot, well, this is physically not correct, not to take into account the saturation dependence in the permeability condition. And then there is something like nonlinear function of the flux. I will explain why I do it. So there are again physical reasons for including the PR action. Okay, then this is the flux, permeability coefficient. U star is the outer pressure. This will appear in the boundary condition. B is the boundary permeability. So the flux on the boundary is proportional to the pressure difference inside. So the classical Robert. And G will be the hysteresis constitutive relation, which I will try to explain now. Yeah, the problem is that we have no a priori control duty of the time derivative of the pressure because of the property that the turning points, the slopes are horizontal. So even though we are able to control theta t in some cases, this does not mean that we control ut. Because even if theta t is bounded, ut can be unbound. So we have to do something in order to get some internal estimates for ut. Now, so the result I would like to show here, when I try to convince you that the result is correct, is that if omega is a bounded Lipschitzian domain, kappa is a Lipschitzian function of x and theta, p is greater or equal than 2, then for a large class of hysteresis operators G, which I will specify later, the initial boundary of the problem admits a solution unique if kappa is independent of the situation. If it does depend on the situation, we don't know. And the boundary data must have some regularity. The boundary permeability is in infinity. Use the outer pressures U star, UT star are at infinity on the boundary. And U0, the initial condition is W to infinity, and compatible with the initial level. This is important. I will show the reason why we need compatibility of the initial pressure and the initial level. And then there is a second theorem which says that if the P in the P pressure is equal to 3 and the permeability is constant, then the initial condition, and if the initial condition has a bounded support in the ball of radius R0, then there exists a unique solution which bounded support again in the ball with radius, which is proportional to T to the 1 over P. So this means that the speed of propagation decreases with time. And so the wetting front propagates, but propagates slower and slower. Now, so the size of the data can be arbitrary. We do not assume a restriction on the size of the data. What we do, so the proof is carried out by this time discretization of the PV with the time step tau positive. And the strategy is to derive sufficient estimates for the time distinct approximations and let time step convergence. Now, hysteresis. What is hysteresis? We use the Pricer hysteresis model, which was introduced by Pricer in 1935 for magnetism, but it works equally well for force medium. So the idea is that the basic building block is the idea of a relay, a switch, which switches between -1 and 1, and it is tuned to some. It is tuned to some value V. So U increases, decreases. When U increases and reaches the value of V plus R, it switches up to plus. And then U decreases and remains +1 until it reaches the value of V minus R and then switches down to -1. This is called a relay with interaction field V, and R critical field of coercivity. And so the porous medium is to be, we imagine the porous medium to be a collection of cells. And the cell can be full or empty, but nothing in between. So it can be +1 means the cell is full, -1 means the cell is empty, but to let the cell evacuate or to fill the cell, you have to overcome a certain resistance, which is expressed by this critical field coercivity R. So we have all kinds of cells with all kinds of interaction fields, all kinds of critical fields of coercivity. And now, so we will show how it works in practice. So this is one relay. This is the so-called Pricer half plane. It's all, so this represents the relays with parameters v and r. So r is positive, v is real number, and so already we assume that initially there is a line v equal to lambda of r. If you are above the line, all switches are -1. If you are below the line, all switches are +1. And now we switch on the input. So u is the input. So here you will see the evolution of the function u as a function of time, and here you will see the evolution of the saturation as a function of u. Okay, so we switch on u, and u starts decreasing. Now, when u decreases, the switches that were -1 remain -1. But the switches that were +1, some of them switch to -1. Which ones? Exactly the ones for which u equal to v minus r, or v equal to u plus r, right? This is this one. So when u decreases, the -1 domain becomes bigger, and theta decreases because theta is given as by an integral over RLS with the probability density v, the positive density. So if the rise decrease, the saturation decreases. And now what happens at the turning point? So you see that u starts increasing. The switches that were +1 remain +1, but some of the switches that were -1 switch to +1 too. And these are precisely the relais corresponding to the equation u equal to v plus r, or v equal to u minus r. And so this means the +1 domain becomes bigger, the saturation increases, but increases along a different curve. And so you see, so it looks like this. You see that, for example, here, there was a minor loop. As soon as the minor loop is closed, it is forgotten. It is removed from the memory. The only thing, the only information that we have about the memory of the system is this curve, this one. And now, so we go up and down, we create more and more memory, and then we erase again more and more memory. So you see that all the local maxima and minima between the absolute maximum and absolute minimum are forgotten. They do not participate in the evolution. And now, but this is the definition. So we would like to learn an analytic description, an equation. And there is indeed an equation, which so there is another experiment 3, which says that the moving interface between the +1 and -1 region in the quasar plane is described by a solution operator of variation inequality. This is the variation inequality, so-called play operator. The play operator is this. If I move the pointer, I want to move the box of the pointer. I move it to the left when I'm on the left side, I move it to the right when I'm on the right side. I don't move it at all. And so this motion is described by a very simple variation of inequality, which is written here. We prescribe some initial condition. This is precisely so for every element. We have all possible boxes of all possible sizes, and each of them is a solution of the variation inequality. This is a typical diagram of the plane. So this is the moving box. There is no motion if we are inside. The motion only takes place going up when we are on the right. Down there, it could go down when we are on the left. And then this means that now the pressure operator was a integral over the relais. What is that? So the relay can be on the +1 or -1. It is -1 if we are above the plane, +1 if we are below the plane. So we can split this integral into two integrals. The domain where the relays are +1, which are below the plane, and -1, which are above, which is nothing but the integral over all possible values of the size of the relay, the nonlinear superposition of the plane operators integrated over R. I have removed the dependence on lambda because just to simplify the presentation. This is something I mentioned at the beginning, that this initial memory configuration has to be somehow in agreement with the initial condition. So this is not that I want to neglect it and just simplify the problems. Okay, so this is now going to be our hysteresis relation, integral over solution operators of this elementary relation. And this relational equality has very nice properties. So, for example, the solution operator of the relational equality, which means also the same for the Paisach operator itself. So they are Lipschitz continuous, both in the space W11 of absolutely continuous functions and in the space of continuous functions. So they can be extended in the space of continuous functions, continuous. And we have, so this is what I said, that if U increases, then G of U increases. So G of UT times UT is greater than G of UT squared. But information about G of U by T does not give any information on UT. UT is bigger. Now, the Paisach operator has very nice properties with respect to the energy balance. So we can define the potential energy of free energy, which is again, this is again an operator, a Paisach type, the difference that the function capital Psi now is positive. So we have a positive free energy, again, in the form of a Paisach operators or function of the plane operators. We can define a dissipation operator, which is again a Paisach operator. And we have the energy balance equation. Now, look at this is indeed an energy balance. What is U? Use the pressure, you use the force. Force times velocity, this is the power supply to the system. Minus potential energy increase, the dissipation. Dissipation is positive in agreement with the circumference. Now, and there is one property that I will use several times, the kind of monotonicity. So the plane operators are naturally monotone because they are solution operators of the monotone relational network. But the Paisach operator is a nonlinear superposition of the place, but it is still monotone, but only with respect to the Heaviside function. It's a function which is 0 for s less or equal to 0, equal to 1 for s bigger than 0. And this was an observation made by Martin Hilbert in 1989. And this is something that is used systematically in the theory of PDEs with spaces. Now, and so the statement is so we can test the difference of GU T minus GUT by the Heaviside function of U minus V, and this is greater or equal than the time derivative of something positive, the positive part of the difference of the distance. Now, the proof is extremely easy. So we take two inputs U and V, we take the plane operators Xi R eta R, they are solution operators of the relational inequalities. Now, we can choose. In the first inequality, we choose Z equal to V minus eta. Here we choose U minus Xi. That is steady too, right? And now we can multiply the equation by something positive. By Xi prime. Xi is an increasing function. So it is still true. And now we can take the sum of the two. And the sum of the two is this. So Xi prime times Xi R dot minus Xi prime of eta R dot minus what is in the parentheses. And now H, the Heaviside function, is monotone. So it will still be true if we replace U minus V minus Xr minus eta R by the difference of the Heaviside functions. But the Heaviside function is a very special function. So the inequality will still be true if you replace the Heaviside function with the Heaviside function of psi of Xr minus psi of eta R. But this is exactly just integrating over R and get exactly the formula of this. Now, and there is another feature of hysteresis of operators, namely the second order energy inequality. So this is something that has been known for 40 years now. That if the Preisach operators have a strictly positive density, then there exists a convexity interval. So there exists some M. The M can be small in typical cases. But we always can find an interval minus M such that if the input does not leave, the range of the input does not leave the interval minus M, the ascending branches of G are uniformly convex, and the descending branches are uniformly convex. And now we take an input U, which is continuously differentiable. We choose U in such a way that G of U is twice differentiable, and then there exists delta such that we have the second order energy inequality. This is indeed something that looks like the energy inequality, only there is one derivative more. So this would be like the counterpart of the power supply to the system. This would be a counterpart of the derivative of the potential energy, and this will be the counterpart of the dissipation, which is of the cubic. I will come back to that, and but of course, this is not very useful for our purposes because we do not have one convex operator. So our convexity domain is typically very small. But if you want to solve the problem with large data, we need something better than that. But this will be an inspiration. Okay. We can exploit this property for large amplitudes of oscillations, but we have to work at it. Now, the problem of diffusion. There are already in the 1980s, there have been results about existence by Augusto Visotil and uniqueness by Martin Hilper for PDEs of that kind. Theta is a theta contains, so this is again the moisture content, it contains the hysteresis operator, the Preisach operator, for example, but it contains also a linear part with C positive. But this is important. This makes the things much easier. You get test value T, you get immediate estimates from the T, gradient of U, etc., and cost to the rate. Now, even in this case, if you have just the Laplacian, but for C equal to 0, we still get a bound for theta t because we test this equation by ut. We have ut theta t, which is something like theta t squared, but this does not say anything about ut. So even in this simple case, we do not have any a priori information about it. And now, this is what I mentioned at the beginning, that if accidentally it happens, for example, in this situation, in C equal to 0, that the Laplacian of U0 is not 0, and the initial memory is such that it corresponds to a turning point, then we cannot expect even a local solution. Because at turning points, theta t is necessarily 0. And so if the memory is such that theta t is 0 and the Laplacian is not 0, we have no solution. So we have to do something, we have to assume something about the machine. And the assumption is the following. This is the assumption. So we do not have the Laplacian, we have the divergence of kappa times P minus 1 power of the gradient. So this is the flux, the divergence of the flux. So if the divergence of the flux which is equal to the saturation increase. So if the divergence of the flux is positive, this means that the saturation is to go. In order to avoid that the memory curve as a turning point means that there must have been in the past, in the immediate past before t equal to 0, an increasing, a possibility of an increasing input which would produce the memory curve. So if the divergence of the flux is positive, there must be a part of the memory curve, of the initial memory curve, its slope -1, and on an interval which is something like the square root of the divergence of the flux. And then we are able to start to say that there is a local solution, then extend the local solution to the group. So this means that the initial condition which for the case with positive or negative flux must somehow correspond to the initial. Good. Yeah, construction of the solution. So how do we? So yes, we define discretize the problem in time. But instead of the time differences, I write simply theta t, for example. When I write theta t, I mean the difference 1 over tau theta I minus theta I minus 1 in an interval t I minus ti. And also theta is discretized as theta I, u is discretized as ui. So these are time discrete, these are constant functions of x. And for test functions in W1, the intersection unit. And now, so what we get, we have the energy inequality. This is for sure. So we test energy inequality, we get the energy inequality by testing the equation by u, and we immediately get gradient of u to the power t in the integral bounded something in the energy, the supplement of the energy. But the energy does not give really relevant information. This is we just know that the energy is positive, not negative. Fortunately, we have the Hilbert inequality, which allows us to test by the Heaviside function of u minus some capital R, with capital R sufficiently bigger, for example, than the right-hand side. Then we prove that the functions ui of x and uxt is globally bounded. This is an additional information, but it's still not enough. Because the weakest one, the largest function space in which the Pavel operator is continuous is L1 omega with values of space of continuous function. So we cannot go further than continuous function. Well, a little bit, we can go to regulated functions, but we do not have better embedding theorems for regulated functions than continuous function. So we need compactness in the space of continuous functions. And in order to have that, we need some estimates for u. Yeah, and so ut has to be estimated in the suitable function space, which is compact dependent in the space L1 with values C0. And this will be the origin. Now, so again, so the only possibility is the complexity estimate, but we need to extend the convexity technique to a larger class of operators. And now, there is one observation that if P is a Kreisach operator is positive density, that if G is an increasing function, then the superposition P applied G of nu equal to P of G of nu is a Kreisach operator. So it is still a Kreisach operator with a different Kreisach measure, but it is a Kreisach. Well, and this is the idea that behind that we do it the other way around. We have the operator here an operator G, and we look for a Kreisach operator P, which is globally convex and which admits an increasing function G such that G of u is equal to P of G of u. And then possibly exploit the convexity of the outer operator. And there are a lot of operators which are convexifiable. For example, the engineers call generalized Kontrashensky operator. This is so if P, Kontrashensky operator P is such that its density function mu of R and the distribution of the RS does not depend on T. It's only a function of R. And this one is global convex. And then if P is a Kontrashensky operator, G is a smooth increasing function, capital G equal to P of G of U is called generalized Kontrashensky operator. And this is something control engineers like them. Because the Kontrashensky operator is explicitly inverted. There is a formula for the inverse of the operator. But this means that we also have a formula for the inverse of the generalized Kontrashensky. Inverse, the superposition is the inverse superposition of the inverse functions. And this is a very large class of operators which, as I said, so electrical engineers, they almost exclusively use generalized Kontrashensky operators instead of Kreisach. And now, so this will be the idea. So we take G convexifiable and exploit the convexity of the convex operator. Now, convexity. So G is convexifiable. G is capital G is P of small g, and P is globally convex. And G is an increasing function. And now we do the same trick as for the convex operator, but instead of we differentiate still in discrete time. So the second derivative is not the second derivative is the second difference. So we differentiate the equation, the test function phi, and we test by a function f of w. And now what happens? Now the boundary term is easy, so this is something that gives control contribution in terms of the. And so there are two terms that need to be considered in detail, namely the hysteresis term and the flux term. Now, so let us start with the hysteresis. So now P is a convex operator. And we test it with f of w. P, w is G of u. Right? Now, in each monotonicity interval of the input w, the operator P behaves like a Niemitzsky operator generated by an increasing function h of w. But h of w is different in each monotonicity interval. So h is strictly convex if w increases, strictly concave if w decreases. But remember, w is G of u. So there will still be some work. Now, okay, so let us continue. This is now, let us take one monotonicity interval represented by a function h. So h is an increasing function, which is convex if wt is positive, concave if wt is negative. And this is okay, this is chain. So chain. And now I don't like this time, but this is again a time derivative of something. So I again integrate by parts or differentiate by parts. And what we get is this. is d by dt. So this is something that I would like to call energy supply to the system. This is something that I would like to call derivative of the free energy. And this is something that I would like to call dissipation. Capital F is the antiderivative. Now, so this is the so-called dissipation. But look, so H is convex and WT is positive. So H double prime is positive and WT is positive. H double prime is negative and WT is negative. This is the convexity of the operator. So I can replace the product by the product of the absolute values, and I can estimate the second derivative of H from below by a constant. So eventually what we get a bound for a function capital gamma. This is the function capital gamma on the right hand side, the dissipation, which can be explicitly written as z times integral 0 to z s f prime plus ds. Now, if f is a linear function, this was the example that I mentioned at the beginning. If f is a linear function, f prime is 1. This will be z squared over 2 times z cubed over 2. This is the cube that I mentioned at the beginning. So this would be very good if we were able to take f prime equal to a constant. Unfortunately, this is only possible in dimension 1. So we have to do something else. Now, we have to estimate, so there was also the elliptic term that has to be estimated from the flux time. Now, so again, general. W is G of energy. So WT is G prime of U times UT times F prime of WT. So this is the gradient of F of WT is this. And this is everything that is the time derivative of the expression in the parentheses. So you see that there are some nice terms. These are the terms which contain the product gradient of UT squared. There is only one of them. So F prime of WT is can be put out of the parentheses. Also the gradient to the power p minus 2 can be put outside. What remains there is the good term, some constant times gradient of UT squared, and then the bad terms, which are possible, which are cubic or even fourth order terms. Now the term in the middle can be eliminated by the Cauchy-Schwarz inequality, and then we eventually get an estimate. So if we are able to find some constants, capital A, capital B, such that this the flux term is bounded from below by F prime of WT, the gradient to the power p minus 2, and then there is this unpleasant term with the minus sign, which is certainly not dominated by the term multiplied by capital A. And now, but we still have some freedom to choose the function f prime. If we choose f prime to be 1 over 1 plus z squared, then ut squared is compensated by f prime. And what we get? So this the term gradient ut squared does not help anymore. But what we get is minus constant times the integral of gradient u to the power p. But we know that it is estimated by the energy estimate. And so we have the convexity estimate, which is gamma of ut. So gamma was the dissipation function. But in our case, since we have chosen f prime to be 1 over f prime of z 1 over 1 plus z squared, then we compute gamma of z, which is something of the order of z times logarithm of 1 plus. This is the best of what we can. And so eventually what the estimates that we are able to get from the convexity considerations is estimate for ut in the orange space generated by this function, by the u times logarithm of 1 plus u, and the LP norm for the gradient of u. And we are lucky because this space satisfying this bound is compactly embedded in the space L1 with values in the space of continuous. So there is a hope that we will be able to pass to the limit with hysteresis. And yes, when the derivatives are bounded in the Orridge space generated by the function v plus v, which is a dual space to the conjugate Orridge space, and the convergence of the derivatives is weak stuff. And now, to pass the limit in the equation, we will start with everybody is here knows that the limit is. So the idea is to test by test function phi, which is u tau, the approximate solution, minus u, the limit in the space L1, for example, but it can be the limit in every LP because the functions you are bounded, uniformly bounded, they converge strongly or they converge in the LP space. And plus the delta y with some delta real parameter and arbitrary test function. Now, the integrity consists in exploiting the monotonicity of the P Laplacian. This expression is positive, non-negative, and this means that you can replace this term, the red term, with a term which does not contain the gradient of ut anymore, u tau. And now we can pass to the limit in this inequality because, as I said, ut converges strongly in L1 with values C0t. G of ut converge strongly, G of ut converge weakly, but ut minus u converge strongly. Here again, ut converge strongly, gradients of ut minus u converge weakly, so we can pass it. And now we pass to the limit with delta. And so you can put delta out of the integral. And now delta can be positive or negative. So if delta is positive, you get less than equal to 0, delta negative greater than equal to 0, so you get the solution of the equation. So we have proved the existence. Uniqueness flows from Hilbert's inequality. Bounded speed of propagation. Now, and so let's just take constant permeability. For non-constant permeability, we do not even have uniqueness, so we cannot even talk about the bounded speed of propagation if we don't have uniqueness. So take kappa is constant and p bigger than. Okay. And we assume that the initial initial pressure and the initial memory have support in a ball B of R0. R0 is much smaller than capital R, and we consider the problem on a big ball BR with zero initial boundary condition on the boundary. So the initial boundary condition is not really physically relevant for also the problems, but the theorem says that we have a unique solution which vanishes outside the ball with a radius which is smaller than it. So the solution is 0 already, some distance from the boundary. So this is a solution of every boundary problem with any kind of boundary condition, normal, rubber, any kind of homogeneous boundary condition. So the initial boundary condition is artificial to construct the solution. And then eventually we will see that this is a solution of the original problem. Good. Enough. So the idea is to fix some constants alpha and c, and we construct a family of explicit solutions depending on the unit vector E of the form capital U. Capital U will be a function of one variable, a real function of one variable of the unknown alpha plus CT minus scalar product dx. And U will be a continuously differentiable function. U of Z equal to 0 for Z plus or equal to 0, U prime of 0 positive for Z positive. And we will try to find a function such that this is a particular solution of one. Now, so the function U vanishes in the half space, scalar product Ex bigger than alpha plus C. And now, E is a solution of the problem if and only if C times C is the speed of propagation. Phi of U, phi is the initial link curve of the Isaac operator is equal to kappa. Kappa is the permeability, U prime of Z to the power P minus. But this is a very easy differential equation. That so we compute the derivative out of that. And now we have to know something about the initial link. Now, so a solution exists only if this integral exists. So the integral of phi to the minus 1, p minus 1 of v dv, if this is an integrable function, and then if this is the case, then we have a formula for u, which is nothing but f to the minus 1 z modular constant. Now, the initial link curve of our Isaac operators is bounded from below from above by functions of the kind v squared over 1 plus v squared. Which means that this condition that the integral exists is satisfied if and only if p is bigger than c. And now, so we, as I said, we take initial data which are bounded in a bounded support, bounded by some term in the domain in the ball bounded by R0. And then we have to guarantee, and so the trick will be using Hilbert inequality. But Hilbert inequality will work only if the initial data of our problem are dominated by the initial data of the explicit solution. And the condition is like the constant C over kappa times 1 over p minus 3 alpha minus tau 0 is bigger than, so this is a fixed constant depending on the initial. And now, so C is the speed of propagation. So if the C can be arbitrarily small, if alpha is sufficient to large. Now, and so this is the variation formulation of the problem, and we subtract. So we have a solution. We have a solution to our initial boundary problem. We subtract our explicit solution depending on the vector which is there E, and it is still 0. And we test this equation on the Harrison function difference. We are back to the quantity again, and we conclude that U is bounded by UE for all directions. But it's the same for minuses. The plus or minus will behave the same. And but UE, in the direction of E, UE vanishes outside of the moving front. And we are moving flows which move with the same speed in all directions, so eventually the solution is bounded in every direction. So the support of the solution remains in the bounded ball in every direction. And now, so this is already said, we get the same for the Roman or Neumann problem. If we take omega sufficiently large so that the ball ranges are with the scale, the relation boundary conditions is inside. And now, so the motion of the wetting front is described by the envelope x equal to RT of the linear functions RC of t equal to alpha plus ct, where alpha is R0 plus k c to the -1 over p minus 1. This was the condition that if c will be small, alpha is sufficiently large, and this is precisely the problem. And now what is the envelope? The envelope is the solution of this ordinary differential equation, which says that the straight lines RC are tangent to the envelope at every point of contact. And so this is you construct the ordinary differential equation that can be solved explicitly. And this is the solution. So this is the motion of the moving from the closed. And that's it. So the conclusions. Convexity makes it possible to derive higher order primary states. And PDs will be studied. For hyperbolic equations, this has been exploited already in the 1980s for the globally convex operators. Locally convex hysteresis in parabolic PDEs restricted to small amplitude motions is of limited interest. But the convexification concept makes it possible to extend the convexity technique in a large data case. And also effects of gravity, mechanical deformations, and so on can be included as well. And there is one reference that I would like to mention, and that's all. Thank you very much.